When it comes to surviving a deadly aerodynamic spin, the battle between Mooney and Beechcraft exposes a terrifying steel tube secret. Every rich pilot in the 1960s wanted the sleek, aluminum Beechcraft Bonanza V-Tail. They thought they were buying the ultimate luxury flying machine, but they were completely ignoring the brutal, unyielding physics of the Mooney M20. Standard airplanes like the Bonanza rely on a thin, riveted aluminum shell, a monocoque, to keep the cabin from crushing. It is literally a flying soda can. Mooney engineers did not trust thin aluminum to save your life. They secretly built a heavy metal, welded steel cage completely hidden under the skin. When the wings stall and the ground is rushing up at 120 knots, do you want to be strapped inside a fragile aluminum shell or an indestructible steel vault? August 14, 1947. Beech Aircraft Corporation in Wichita, Kansas, rolled out the Model 35 Bonanza and landed an FAA type certificate that would haunt accident investigators for decades. The sales pitch was pure post-war bravado. Ads flaunted a 160-knot cruise, a V-tail that looked like it belonged on a fighter, and a cabin trimmed for doctors and oilmen who wanted to park their money on the ramp. The Bonanza became the gold watch of general aviation, a flying status symbol for men who measured self-worth in knots and chrome. But the aluminum shell they paid for, the so-called semi-monocoque fuselage, was a thin, riveted pressure vessel built for speed, not survival. Underneath the glossy paint and stitched leather, the structure was a calculated risk: 2024 T3 aluminum skin riveted to a skeleton of stringers and frames, designed to just barely meet the FAA ultimate load factor. The Model 35's V-tail, made of magnesium alloy, was a marvel of efficiency on paper, but a nightmare for anyone who understood torsional rigidity and mass balance tolerances. Meanwhile, Mooney International Corporation down in Kerrville, Texas, watched the Bonanza's parade of wealthy buyers with a mechanic's contempt. Mooney engineers did not trust fashion or the FAA design minimums. They wrapped every M20 cockpit in a welded 4130 chromoly steel tube cage and ran a continuous main spar under the cabin, a structure that cared nothing for luxury but everything for crash energy paths. The result? A door on a Bonanza closes with a hollow click. A Mooney's slams with the blunt finality of a vault. The difference is not just sound, it is the difference between a kinetic energy coffin and a meat locker that might actually save you. In the rush to own the skies, too many Bonanza buyers never asked what happened when the paint got torn off and the rivets started popping like gunfire. Status symbols do not survive a spin. Structural philosophy does. Kerrville, Texas, did not have Wichita's swagger or the endless parade of salesmen in pressed suits, but it had something Beechcraft's chrome and leather crowd never understood: a corporate culture that treated every crash photo like a blueprint for survival. At Mooney International, the engineering floor was not a place for dreamers. It was a steel and spar monastery where every inch of the M20 skeleton got the same paranoid scrutiny as a racing roll cage. The Bonanza buyers wanted to be seen, Mooney customers wanted to walk away. That is why the M20 cockpit sits inside a welded 4130 chromoly steel tube cage, a design philosophy that cares less about polish and more about what happens when the world goes sideways at 120 knots. This was not just a different material choice, it was a different world view. Beechcraft Model 35, born in Wichita's war boom. Optimism, trusted aluminum skin, and the promise of ultimate load factors certified on paper. Mooney's team in Kerrville, hardened by the memory of airframes peeled open like sardine cans, ran a continuous main spar right under the pilot's knees, a single unbroken path for crash energy as if daring physics to try its worst. The result is a structure that does not just meet the FAA minimums, it sneers at them. When you slam a Mooney door, you hear the echo of steel tubes locking into place, a sound more vault than vehicle. That is the hidden divide, one airplane engineered to impress ramp rats, the other built as a kinetic meat locker, ready for the day the rivets let go and the glamour bleeds out. The question is not which looks better in a hangar. The question is which cabin you want wrapped around you when the spin will not stop. The Bonanza's semi-monocoque fuselage is a masterclass in calculated risk, not brute strength. Beech Aircraft Corporation in Wichita, Kansas, built the Model 35 as a pressure vessel made of 2024 T3 aluminum, a metal with a tensile strength of about 483 megapascals. That sounds impressive until you realize what happens when you push it past the Federal Aviation Administration ultimate load factor. The skin is thin, measured in thousandths of an inch, and every ounce of weight shaved off for speed comes back to haunt you in a spin. When the load spikes, the aluminum does not yield gracefully. It buckles. The rivets, those proud rows of domed heads, start to fail in sequence. Under high stress, they do not just let go, they detonate. You hear it in the wreckage, rivets popping like bullets, the skin shrieking as it tears, the whole pressure vessel collapsing inward. It is the sound of a soda can being crushed in slow motion. At 120 knots, the violence is anything but slow. The semi-monocoque relies on the skin to carry the load, with stringers and frames acting as little more than ribs in a thin-walled drum. Once the skin buckles, the load path vanishes. There is no redundancy, no inner skeleton to take over. The failure is rapid, total, and ugly. You can trace the path of collapse in the wreckage, a line of torn rivet holes, a buckled panel, a pressure vessel that has lost all geometric integrity. The aluminum does its job right up to the edge, then fails catastrophically. This is why every Bonanza accident investigator knows the term rivet shriek line. It is the forensic trail left behind when the skin gives up the fight. The structure is optimized for weight, not for mercy. In a spin, the Bonanza's cabin is a kinetic energy shell that holds together until it does not. That is the trade-off of the semi-monocoque. Efficiency at altitude, fragility in the ground rush. The difference between a vault and a soda can is not just material, it is the sound you hear when the loads go sideways. Welded 4-130 chromoly steel. That's the Mooney M20's secret weapon, not a fashion choice. In Kerrville, Texas, they didn't chase magazine covers or the applause of ramp rats. They chased survivability. The steel tube cage at the heart of every Mooney isn't just a nod to racing roll cages, it's a calculated rejection of the semi-monocoque gamble that Beech Aircraft Corporation made in Wichita. Each tube is cut, mitered, and TIG welded into a triangulated lattice, geometry borrowed from the world of crash-tested race cars and warbirds. You can spot the difference the moment you strip the skin. Where a Bonanza's structure looks like a soda can with ribs, the Mooney's cabin is a fortress of steel triangles, each joint a node that spreads load across the entire cage. The 4-130 chromoly alloy, chromium, molybdenum, and a dash of carbon, offers tensile strength up to 970 megapascals and a yield strength that laughs at the numbers stamped on 2024 T3 aluminum. This isn't just about brute force, it's about fracture toughness. When an impact comes, the Mooney's cage flexes, distributes, and absorbs, refusing to crumple inward. The continuous main spar, forged from the same philosophy, runs wingtip to wingtip beneath the floor, tying the structure together in one unbroken load path. In a crash, the energy follows the spar and the tubes, not the skin. That's why a Mooney door slams shut with the cold, echoing finality of a bank vault. The welding geometry matters. Every gusset and diagonal is placed to redirect shearing forces away from the pilot's knees and toward the strongest parts of the frame. The result is simple. When the skin is torn away, the cage is still there, holding its shape, giving the meat inside a fighting chance. Mooney's engineers didn't trust the Federal Aviation Administration's minimums or the promises of ultimate load factor on paper. They trusted steel, continuous structure, and the ugly, low-slung stance that keeps the center of mass anchored to the earth. That's not pretty, it's not marketable. But it's why, when a spin turns into a ground rush, the Mooney's vault stays closed while the soda can folds. On paper, the FAA drew a neat line. Both the Beechcraft Model 35 Bonanza and the Mooney M20 were certified to survive the same ultimate load factor, 5.7 G. That's the number stamped on the type certificate datasheet, the bureaucrat's idea of parity. But anyone who has ever picked through the twisted bones of a crash knows the real story is not in the paperwork. It's in how each airplane handles that number when the world goes sideways. The Bonanza's semi-monocoque fuselage, all 2024 T3 aluminum skin and riveted frames, is a marvel of efficiency right up to the edge. Push it past 4.4 G, the design limit, and you can hear the structure start to give up. Rivets detonate in sequence, the skin buckles, and the pressure vessel collapses inward. The ultimate load factor is a theoretical ceiling, but the Bonanza's margin is razor thin. Once the skin goes, there is no inner skeleton to catch the load. The torsional stiffness of the V-tail, already compromised by magnesium ruddervators, drops off a cliff the moment flutter sets in. That's why, when a panicked pilot yanks back at high speed, the empennage can twist itself to pieces before the altimeter even catches up. Now, Kerville's answer is the Mooney M20. Welded 4130 chromoly tubes form a triangulated cage, wrapped around a continuous main spar that runs wingtip to wingtip. That structure shrugs off loads up to 5.7 G and keeps its shape when the skin is torn away. The torsional rigidity is real, not just a number. Steel does not crumple like soda can aluminum. In a spin, the Mooney's cage flexes, absorbs, and redistributes, refusing to fold. The FAA might see two airplanes built to the same standard, but in the kinetic meat grinder of a flat spin, only one acts like a vault. The other, no matter how pretty, folds like a trophy case dropped from a ladder. Push a Bonanza V-tail past its never-exceed speed, and you do not get a warning light, you get physics cashing in a debt. The magnesium ruddervators, those featherweight control surfaces Beech Aircraft Corporation bragged about in every sales brochure, are a flutter trap waiting to spring. The moment airflow hits that critical speed, sometimes just a handful of knots over VNE, the tail starts to tremble. It is subtle at first, a vibration through the yoke, but in less than 3 seconds, the oscillation goes exponential. The whole empennage becomes a tuning fork, the frequency rising until the magnesium skin cannot keep up. Torsional rigidity, the only thing standing between control and chaos, drops out. The rivets in the rear spar start popping like popcorn, the aluminum shrieks, and then the tail tears away with a violence that is almost surgical. Aeroelastic theory calls it a self-excited instability, but in the wreckage, it looks like a bomb went off at the hinge line. The NTSB has measured this sequence in the lab, from first oscillation to total separation. It is 2.5 seconds, maybe 3 if you are lucky. There is no time for a mayday, no second chance for a panicked pilot who yanked too hard or let the nose drop in a dive. Once the flutter starts, the magnesium gives up. Its fatigue limit is a joke compared to 4130 chromoly, and the tail is gone before the altimeter even catches up. This is not a design flaw you can blame on a single bolt or a bad batch of alloy. It is the price of chasing speed and style with a structure that is efficient on paper but brittle at the edge. The Bonanza's V-tail, for all its mid-century glamour, is a kinetic energy shell with a hair trigger. The flutter envelope is not a rumor, it is a hard boundary. Cross it, and the airplane decides who walks away. Flat spin is not just a phrase in the NTSB report. It is the moment when the airframe's promises run out and physics takes over. In a Bonanza V-tail, the transition from a routine stall to unrecoverable chaos can happen in less than 5 seconds. The magnesium ruddervators, already flirting with their fatigue limits, start to vibrate as airflow wraps around the tail in a tight, deadly spiral. The pilot, usually a weekend warrior with more money than flight time, yanks the yoke and stamps the rudder, but the controls go slack. That is the signature of a flat spin. The airplane rotates around its center of gravity like a dinner plate on a stick, centrifugal force pinning the meat in the seats to the outside wall while the nose stubbornly refuses to drop. Inside the cabin, there is no sense of up or down, just the shriek of airflow and the metallic percussion of rivets letting go. The semi-monocoque fuselage, so sleek on the ramp, becomes a pressure vessel under siege. The aluminum skin, optimized for cruise, starts to ripple and buckle as the loads spike far beyond the FAA's ultimate load factor. There is no backup structure. Once the skin gives, the whole shell implodes, sometimes before the altimeter even has a chance to wind down. The V-tail, caught in its own aerodynamic feedback loop, can lose effectiveness entirely, trapping the airplane in a yaw-pitch coupling that even test pilots dread. Recovery is not just difficult, it is nearly impossible for anyone caught off guard. The control coupling in the Bonanza's V-tail means that rudder and elevator inputs blend together, so the classic spin recovery, full opposite rudder and forward stick, has to be executed with split-second timing and nerves of steel. Most never get the chance. In those final moments, the Bonanza's reputation as Dr. Killer is not about weak metal or bad design. It is about an unforgiving airframe that punishes hesitation and rewards precision. The myth is that the V-tail was cursed. The reality is that it was a machine that demanded respect and punished the lack of it with catastrophic kinetic clarity. FAA Airworthiness Directive 94-20-04, Revision 2, landed like a verdict. The directive's language is blunt: inspect every ruddervator for fatigue cracks, bolt hole elongation, and the first hint of failing magnesium skin. Stainless steel reinforcement plates and lock washers are now mandatory. Inspections repeat every 12 months or 2,000 hours. Form 4500-15 becomes a permanent entry in the logbook, a reminder that ignoring the flutter envelope is gambling with the airplane's life. The FAA's fix was not a redesign, it was a patch, bolted on after too many Bonanzas lost their tails in sudden, catastrophic dives. Mooney's approach in Kerrville was the opposite of a regulatory rescue. Every M20 left the factory with a welded 4130 chromoly steel tube cage and a single, unbroken main spar stretching from wingtip to wingtip. The cabin sits low, not for looks, but because a low center of gravity and a spar under the seats keep leverage in check when things go wrong. This geometry is not about style, it is about survival. The M20's design refuses to flip, even if the gear collapses or the ground comes up fast. No FAA directive ever forced Mooney to reinforce the cage or spar. They did it from the start, having seen what happens when structure fails. Defect protocol. The Bonanza survived by mandate, patched after disaster. The Mooney was built to pass the test before it began. One is a rescue plan. The other is a philosophy written in steel. Count the bodies, count the breakups, then normalize for hours flown and see who's really playing Russian roulette with their tail. The Turner spreadsheet doesn't lie. 27 documented V-Tail Bonanza empennage separations occurred from 1962 to 2007, with 3 more since, for a total of 30. That's 0.018 in flight tail failures per 100,000 flight hours, or about 1.5 catastrophic breakups per 1,000 airframes. Now stack that against the straight tail Bonanza, 4 tail-related failures in a fleet that has flown nearly 1 billion hours for a rate of 0.003 per 100,000 hours. The Mooney M20, 0 documented empennage separations, not a single NTSB docket showing a steel tube cage torn open by a flat spin or flutter. When you normalize for exposure, the V-Tail Bonanza carries a 6-fold higher risk of tail separation than its straight tail sibling, and the Mooney's steel vault sits in a statistical league of its own. The numbers aren't folklore, they're the grim arithmetic of kinetic energy and structural margin. Status symbols fold, vaults hold. Steel versus aluminum, here is the final word, and it is not even close. You can comb through every NTSB docket from the last 60 years, tally every twisted Bonanza V-tail, every magnesium ruddervator flutter, every broken promise of ultimate load factor. The numbers land like a hammer. The Bonanza 5-tail racks up 30 documented empennage separations with a rate 6 times higher than its straight tail sibling. The Mooney M20 0. Not a single NTSB report, not one docket, not one case of a welded 4130 chromoly cage or a continuous main spar letting go in flight. No steel tube cabin torn open by a spin, no survivors crawling from a shredded vault, because the vault stays closed. That is not luck. That is what happens when you build a kinetic energy cage instead of a pressure vessel that folds like a soda can. The verdict is ugly, blunt, and written in the wreckage. In the arena of unrecoverable spins, the Mooney's steel tube cabin is the only design that never fails. You want to walk away when the loads go sideways? Pick the airplane built by paranoid mechanics, not by marketing men. That is the mechanic's verdict. Vaults hold, soda cans fold. Today, you can still buy a Bonanza V-Tail. Just hope you never hear the tail rivets snap like popcorn above VNE. For all the country club bravado and Wichita polish, the real verdict sits in NTSB crash data, 4130 chromoly cages. Outlast aluminum monocoques when kinetic energy goes unspent. In this business, the only luxury is structural redundancy. The vault saves the meat. The soda can folds. Decide what you are strapping into.